Good afternoon, everyone. I hope you've injected yourself with a little bit of caffeine so that I can put you back to sleep with my talk. All right. So today I'll be talking to you a little bit about modeling of cementitious systems. I think the topic of the lecture that was given to me was thermodynamic modeling. But before we jump into thermodynamic modeling, I thought I'll give you a little bit of an overview of modeling and the history of modeling of cementitious systems, right? So broadly in this talk, I'm going to cover three objectives. The first is to understand why we model anything and why we model cementitious systems, concrete in particular. The second is to look at the various tools throughout history and in the modern era that are available for us to model cementitious systems. And the third is to look at some of the examples of applications of the thermodynamic modeling tools that are available to us, right? So I was actually not going to present this slide, but yesterday over dinner, Professor Anup convinced me that this is a good slide to have. So this is essentially to try and represent to people unfamiliar with what a model is, the concept of modeling. So a model is any mathematical representation of a physical reality, right? So for example, if you look at the map of Delhi Metro that's been posted in one of the signboards outside the metro station, it's all nice. It has some nice concentric circles. It has straight lines, etc. But if you look at the actual Delhi Metro line map, right, it's not a concentric circle. At every few 20, 30 meters, you have some variations. It goes down in depth. It comes back up. Some of the stations are under the ground. Some of the stations are above the ground, etc. Right? But this does not capture that information. Right? Yet, this mathematical representation, we call this a graph in mathematics. So this mathematical representation is very useful for us. If I give you a map that looks like that, and I tell you, okay, you need to get from Gurgaon to Noida, you'd be hard-pressed to figure out which station I should get into and which station I should get out of. But if I give you a map like what is shown on the left-hand side of this slide, right, you'll know that, okay, I need to start at the yellow point. Okay, I'll use the pointer. I have to start at this yellow line somewhere here, go up, take this line, and then take the blue line here and get down at Noida, right? So are models exact representations of the physical reality? No. They are mathematical approximations of the physical reality that are somehow useful to us, right? So does it have to be exact? No. Does it have to be useful? Yes. So models have to be useful. A good mathematical model balances the physical accuracy with the usefulness and the mathematical representation that we use, all right? So a couple of questions. Why do we even model anything? Right? I just said it's a mathematical representation of a physical phenomenon. Why do we want to model anything? We can just keep doing experiments and figuring things out, right? So why do we want to model anything? Any ideas? Amit, don't answer. Your entire PhD was on modeling, so I don't want you to answer. I want someone else. Any idea why we model? Okay, we didn't give enough coffee to them, I guess. Okay, so essentially, you gave a great answer. So I'll break your answer into two parts. The first is you said that you can predict outcomes, right? The second is experiments are usually time-consuming, labor-consuming, money-consuming, etc. And using modeling, if you're able to predict, you can save some costs, right? Yes. In fact, the first point that I have is predicting the behavior, right? Predicting the behavior in circumstances when we are able to experiment and in circumstances when we are not able to experiment, right? For example, eclipses. Some of the earliest models that were known to humanity were geometric models drawn in sand with lines that essentially helped ancient humans predict when sun, moon, and all would move across the sky, when there would be eclipses, etc. Right? These are some of the earliest models that are available. When the Romans started designing bridges, and I don't know if this is an urban legend or whether it actually happened, but there are instances where I've read that they used to make the engineer who designed the bridge stand under the bridge while the chariots rode on top, right? I'm not comfortable doing that in today's building climate, but yes. So the Roman engineers would use geometric designs, etc., to make sure that, okay, I'm not going to die when a chariot goes above me, right? You can use it to model deflections, material selection. In high temperature aerospace applications, when you're looking at jet engines, it may not be feasible to do experiments at such high temperatures, at such high wind velocities, combustions, etc. So you can use models to try and predict how the materials would behave at that temperature and then appropriately select your material, right? The second is experiments can be time consuming and expensive. right? Imagine I had to test every single combination of breadth, depth, and reinforcement area for a beam to calculate the bending moment, the moment carrying capacity of the beam. It would get very expensive very fast, right? So models can help us cut down on time and cut down on costs when we want to save resources, when we want to save time, and it can help us predict the performance, right? Is this still working? Okay, great. Models also help us gain insight into the system. So what do I mean by models help us gain insight into the system? There are several cases in chemistry, physics, pure sciences, etc., where we are not able to understand why a system behaves the way it does until we actually develop a model for it. Some examples are general relativity, special relativity, right? Orbital theory in chemistry. They are all examples of models where we didn't understand why atoms and galaxies behave the way they do until someone came along with a mathematical representation that explained the reason for this, right? And finally, generally, we want to do some sort of controlled parametric analysis, which may not be possible in the real world. So if I want to vary one specific parameter without varying any other parameter, you can do it easily in a model. You cannot do it that easily in reality, all right? So now, why do we want to model concrete? The same 4 reasons. We want to predict the behavior. So for example, we want to predict the mechanical behavior. We may want to predict the service life. We may want to predict the durability of reinforced concrete, right? And it's expensive and time consuming to do the entire parametric series of analysis of every single water to cement ratio, SCM chemistry, SCM replacement level, aggregate characteristics, etc. So we can use modeling to save time and judiciously design our experiments to essentially predict the concrete behavior. We can also use models to gain insight into the system, and Aslam will talk to you a little bit about some of the modeling tools that are available that let us gain insight at the nanometer and micrometer level. And of course, we can also do controlled parametric analysis. For example, if I want to look at how the silica content in a fly ash affects my concrete properties, it is very difficult to get multiple fly ashes where every other property like the alumina content, calcium content, reactivity is identical with only the silica content varying. But in a model, I can just hypothetically assume that the silica content varies, and I can use that to my advantage and model how the properties of concrete change, right? So we may, all right. So we may think that, okay, modeling is new. It's everyone's now talking about thermodynamic modeling since the Swiss team has popularized it from 2007. Now everyone's talking about modeling. Let's do modeling. It's new. It's actually not that new. So if you look at your IS codes, right? How many of you are familiar with the relation between strength and water to cement ratio? How many of you are not familiar with that? Let me put that thing, right? So all of you are familiar with the relation between strength and water to cement ratio, right? That comes from the work of Duff-Abrams. It's called Abrams' law or Abrams' model, right? So what you have been using all your life to design your concrete mixtures is actually based on a model. So today we're going to talk about some of those models that have come through history. Every equation that you use to design reinforced concrete beams in IS 456 comes from models. These models can be empirical, which is just curve fitting. They can also be more fundamental based in mechanics and mathematics. But nevertheless, the equations that you use every day are models because they are mathematical representations of your physical reality, right? Some of the earliest relations that you have in civil engineering and engineering in general is the relation between strength and porosity. These were some of the earliest relations that were developed because people wanted to know the strength of different materials, specifically ceramics, inorganics, organics, etc., without having too much of experiments to do. If you have precious little sample, you want to be able to predict the strength without destructively testing, etc., right? So in most, what scientists found was that in most materials, there is a fundamental relationship between the compressive strength and the porosity. So they found that if you plot your compressive strength versus the porosity in the material, you get some sort of an exponential decay curve over here. And they used to generally just model it over here where compressive strength or relative strength, whether it's compressive, flexural, tensile, whatever it may be, is some constant multiplied by exponential decay function with another constant and the porosity inside it. Then people extended this to have a more general term where apart from porosity, you also had like connectivity within the solids, pore size distribution, etc. But these were some of the first models that were developed. That is the link between compressive strength and porosity. Coming to the world of concrete, some of the first models that were developed for concrete, again, models are not new. Ferret's model was in 1892. Sorry, it's not 1982. It's 1892, right? 1892 is how many years old? How much? Maybe 123 years old? 123, 124 years old? So we are, no, wait, 140. We're almost coming up to 150 years of Ferret's law, right? Maybe we should organize a conference for that, right? Anyway, right? So Ferret's law was one of the earliest relations that essentially linked the compressive strength. Oh, I have the wrong plot here. Sorry. It linked the compressive strength of concrete to the volume of cement in your concrete. So Ferret essentially stated that the compressive strength of placeable concrete is directly proportional to the volume of cement in the space that is available to it. So he essentially said that if I have a concrete with some air, water, cement, and aggregate, the space that is available is everything other than the aggregate here, right? So the compressive strength depends on the amount of cement that I have in my space that is available. So he said that compressive strength is some constant times the volume of cement divided by the volume of space that is available. And intuitively, you've gone through the hydration lectures that Professor Shashank and Professor KVL and Srijit have taught you. So you would intuitively now understand that cement reacts with water. So the more cement I have, the more hydration products I have, which means the more strength that will be there. And this was also what Ferret found in 1892. And he developed this sort of a quasi-empirical relation between compressive strength and the volume of cement in the system. Abrams came along in 1919, almost about 30, 40 years later, and he slightly modified this relation. He said that it's not just a function of the volume of cement. It actually depends on something a little more fundamental, which is the amount of water to the amount of cement. The ratio of the amount of water that you add to the amount of water that you add to the amount of cement that you add. And he developed another empirical relation, which was essentially compressive strength is some constant divided by another constant to the power of water to cement ratio. And thus we get the curve that we are all familiar with in almost all international codes, BIS, ACI. I'm sure even the Eurocode has a relation like this, where you have a plot of compressive strength versus water to cement ratio, and you have this nice curve over here, right? This curve, what Abrams also noticed was as this curve went up, right, that at lower and lower water to cement ratios, his model predicted higher and higher compressive strength, but in reality, you are not able to get that. And that is because of the reduction in the amount of compaction that you can get. If you have very low water to cement ratios, you will not be able to compact your concrete properly. You'll have a lot of honeycombing. You'll have a drop off in strength. So he developed a second modification to that curve where you see that as you decrease your water to cement ratio, your strength goes up. And if you're not able to compact it, your strength starts dropping off again, right? But both of them, that is Ferret and Duff-Abram, they both used the water to cement ratio or the volume of cement as a surrogate for the porosity of your concrete. So essentially, the more your cement, the less porosity you have at 28 days. The lower your water to cement ratio, the less porosity you have at 28 days, which is why you get a higher strength, right? In the 1940s, Powers and Brownyard, two researchers from the Portland Cement Association, came along and they said, hey, there is something more fundamental than just the porosity or the water to cement ratio or the volume of cement. They said that it is not just the total porosity, it is the volume of capillary pores. How many of you remember the morning lecture where Professor Shashank talked about gel pores, capillary pores? Only one. Excellent. So maybe we should have given them tea again before your lecture. All right. So just a quick recap. Gel pores are the smallest pores in your concrete. Gel pores are the pores that are associated with your reaction products, so the pores that are present in your CSH, the interlayer spaces, etc. Gel pores are usually under a Kelvin radius of about 5 nanometers. Capillary pores is the leftover space after the cement hydrates. So capillary pores are usually larger than 5 nanometers, and typically they are a couple of microns across, about 10 to 20 microns across, right? 5 nanometers to 10 microns across. Air voids can be entrapped or entrained. Entrapped air voids is essentially due to compaction issues. Entrained air voids is something that we want there. So due to freeze-thaw life, we may add an air entraining admixture, which intentionally entrains air voids into my system. All right. So gel pores, being the smallest pores in the system, they are an inherent integral part of the gel structure. They are usually responsible for properties like transport through the gel, but again, it's an insignificant portion of the total transport through the gel, some amount of elastic modulus, but mainly creep and shrinkage properties. Capillary pores are your larger pores. Being the larger pores, they are primarily responsible for your compressive strength, transport of fluids, transport of ions, sorptivity of your concrete, etc. Air voids, if they are entrapped air voids, they significantly negatively impact your compressive strength. Entrained air voids do reduce your compressive strength, but not as much as entrapped air voids. Entrained air voids are important because you can increase your freeze-thaw life of your concrete if you have them. All right, that was just a boot camp of the 1.5-hour lecture that Professor Bishnoi gave you today morning. So the important pores in this for predicting compressive strength is the capillary pores, because they are the larger pores and they are the empty space that is available after your binder has reacted. So these are a few micrographs and a schematic here. So as your cement reacts and forms reaction products, you have some empty space which is filled with your capillary water. So this empty space between the reaction products is what we call as capillary pores or capillary voids, right? They are usually about 5 nanometers to a couple of microns across, and they are the ones that control your compressive strength. So Powers inherently recognized that it is the total volume of this capillary pores that controls your compressive strength. He also recognized that your compressive strength should be proportional to the volume of gel that forms in the space that is available for it. So he coined a term called the gel to space ratio. The gel to space ratio is nothing but the volume of gel that has formed in the space that is available for the gel to form. So if I take this system here, this nice sketch over here, where I have unreacted cement, I have some reaction products, I have capillary water, the space that is available is the entire thing minus the volume of unreacted binder, because unreacted binder is a very stiff inclusion. So if you look at Powers' papers from the 1940s, he says that, okay, this is the space that is available for the reaction products to fill. Take the volume of gel divided by the volume of space, and you have something called the gel to space ratio. He then plotted the compressive strength of mortars and concrete versus the gel to space ratio, and he found a very good fit. And he developed a relation where the compressive strength is related to some constant multiplied by the gel to space ratio cubed. Right? This model is still used by many researchers and many field practitioners alike. And even today with modern cements, you are able to predict the compressive strength to within about 10 to 15 MPa. 10 to 15 MPa might sound like a huge deal, but compared to other empirical relations at the time, this was a much needed advancement. All right. Now, recently, there have been other advancements that let us use micromechanical models, computational models, coupled micromechanical finite element modeling schemes, multi-scale modeling schemes, etc., that allow us to actually predict the compressive strength to within 5 MPa. In these modeling schemes, again, just to give you a big picture overview without going into the details, you look at the reaction products that form, you look at the mechanical properties of each of these reaction products that form, the CSH, the ettringite, monosulfate, carboaluminates, etc., and then you homogenize them. And using multi-scale algorithms, you essentially compute the compressive strength. And as you can see from this, this is a plot from Pipat's work. You can see that you're able to predict the compressive strength very accurately using these models. All right. So in the past 15 minutes, I've given you an overview of why we model and some of the models through history. So now I'll try to cover a little bit of thermodynamic modeling as well. Right? So you all would have learned how to do these hand calculations, right? I think it would be 10th grade chemistry. You all would have learned how to do these balancing of chemical reactions. So if I have sodium hydroxide and hydrochloric acid, if I have sodium hydroxide and sulfuric acid, how do you do the balancing? You can do a mole balance, mass balance, etc. You can do these hand calculations and calculate how much of each of these reaction products form. So if I have the first reaction, C3A reacting with gypsum and water to form ettringite, you can solve it. Anyone who's solved it already by looking at it? No? Okay, never mind. To save time, I'll just skip. So it's basically you just balance the moles and you solve these reactions. You can solve individual chemical reactions this way. And this term is usually called either mass balancing or mole balancing. It is a very popular tool. You learn it in high school, you repeat it in college, etc. And it's still used in some parts of the cement chemistry world where you want to calculate the amount of CSH that forms, etc. through a simple back of the envelope calculation. What are the advantages of this approach? Advantages, anyone? Very simple to do. It's simple to do as long as you know the molar mass of each of these, right? Or if you know the chemical reaction that takes place, it's very simple. It's a back of the envelope calculation and you can do it. The disadvantages are you need to know the exact reaction that takes place. You need to know the formula of the compound, etc. What if I have a compound with variable stoichiometry like CSH, right? It's difficult to do with mass balance because I don't know the calcium to silica ratio. So without knowing the reaction product, I don't know how to balance my chemical reaction, right? Where's this? The second disadvantage is if I have multi-component systems, it is very difficult to predict which reaction will take place first, which reaction will take place next, what is the preferred chemical reaction. So for example, in the first two examples that I gave you, C3A is independently reacting with gypsum, and in the second reaction, C3A is independently reacting with calcium carbonate. Now, what if my system contains C3A plus gypsum plus calcium carbonate? And let us say I have an excess of all of them, right? Which reaction takes precedence? How much of ettringite forms? How much of carboaluminate forms? Does all the C3A react with gypsum to form ettringite? Does all the C3A react with calcium carbonate to form monocarbonate? Any of you can, bet your life savings on it? No, right? It's very difficult. So when you have multi-component systems with competing chemical reactions, it's very difficult to do this. This is where thermodynamic modeling enters our realm, or enters our lecture, right? With the advent of computing, you can actually now start looking at different chemical reactions in multi-component systems and start predicting which reactions are favorable. And if you have different reactions that take place, how much of each reaction takes place. Thermodynamic modeling is, again, it's not a new thing. It was developed in the 1800s for engines, and then it got modified for chemical reactions, etc. It's been through the works for almost 150, 200 years now. But essentially, it relies on the principle that chemical reactions can spontaneously occur if the reaction products have a lower Gibbs free energy than the reactants. So whatever combination of reaction products gives me the lowest state of energy for the system, that is the reaction product that forms. And the thermodynamic modeling tools that we use today essentially rely on this 19th century principle that minimum energy state is the stable state. All right. So if we look at any of the thermodynamic modeling tools, be it GEMS 3K or FreeQC or any of the other tools that are available, they essentially rely on minimizing your Gibbs free energy of your reaction products. So I'll walk you through with a very simple example. Okay, this is not working again. All right. Yeah. I'll walk you through again with a very simple example. So let us say I have 1 kg of cement and 400 grams of water. And let us say my cement has this chemical composition, 425 grams of C3S, 325 grams of C2S, 80 grams C3A, 70 grams C4AF, a bunch of alkalis, and some gypsum. All right. Now, how do I know what reaction products form? How do I know what is the preferred reaction, etc.? Right? The thermodynamic modeling tool essentially first takes an initial guess at the different reaction products that can form. So for example, let us say our guess 1 is 500 grams of CSH form, 400 grams of calcium hydroxide, 200 grams of monosulfate, 200 grams of calcium aluminate hydrate, magnesium hydroxide, and we have 100 grams of pore solution remaining. Right? So let us say these are my initial guess. In the initial guess also, it's subject to the constraint that you maintain the mass balance and the mole balance of individual chemical reactants. So the number of moles of calcium, silicon, oxygen, etc. should be constant. We then calculate the Gibbs free energy of this combination of reaction products. We then iterate. So we essentially slightly vary the chemical composition subject to the same constraints. We calculate the Gibbs free energy again, and we repeat this process hundreds of thousands of times, and we find the chemical composition that is essentially that essentially has the least Gibbs free energy, right? So the combination of reaction products that has the least Gibbs free energy is considered to be the reaction products that form. And this process has been validated for quite a long time. I think if memory serves me right, one of the first papers that was published in this realm was in the 90s, where they essentially demonstrated that it works. And at chemical equilibrium, they were able to find that thermodynamic modeling is able to predict what you see in the experiments in chemical equilibrium. So when we take the first guess, I told you that, okay, let's start with CSH, calcium hydroxide, AFM, calcium aluminate hydrate, etc. What if I don't know what reaction products form? Will it still work? The answer is yes. Usually your thermodynamic modeling tools are coupled with something that we call a thermodynamic database. So a thermodynamic database is essentially a database of all possible reaction products that can form in your cementitious systems, as well as their thermodynamic properties. Thermodynamic properties like Gibbs free energy of formation, enthalpy of formation, specific heat capacities, the variation of specific heat capacities with temperatures, etc. The software then uses a combination of optimization algorithms and the thermodynamics equations to then calculate what reaction products will form, the chemical composition of those reaction products, as well as the amounts of those reaction products that form at thermodynamic equilibrium. So modeling is great. So let's all do modeling. Hang on. As with any tool, modeling is a tool. It's a mathematical representation of a physical reality. That means it's an approximation. Right? There are advantages and disadvantages. Advantages is we can predict the reaction products at completion. We can predict the total chemical reaction that takes place, the volume and composition of the solid and liquid reaction products. We can predict hypothetical scenarios. We can essentially play with what if scenarios. Hey, what if my reactivity of fly ash increases? What if my halite in the cement is lower? What happens in those cases? I can do all of that, right? But the disadvantages is these tools can only predict compounds that are present in your thermodynamic database. So before you run off and start simulating your system, if it's a typical OPC plus SEM system, the Swiss team and the other teams internationally have done a great job of putting together a list of the reaction products that usually form as well as their thermodynamic properties, so you're able to get a reasonable estimate. But we have had cases where we have fly ashes that essentially produce, let's say, sulfite-containing phases, etc., which are not in the thermodynamic database, which then you need to develop the thermodynamic properties for and add them to the database. So you can only predict compounds that are present in the thermodynamic database. So make sure that you're using systems where you have these compounds, right? The second disadvantage is you can only predict it at thermodynamic equilibrium. There is no mention of kinetics in your by default thermodynamic, there is no mention of kinetics by definition at thermodynamic equilibrium, because the definition of thermodynamic equilibrium is essentially a state where there is no net mass transfer or no net energy transfer, which is your final reaction products that form. Now, teams across the globe have essentially developed approaches where you can combine kinetic models with thermodynamic models to predict the reaction products as a function of time. And for want of time over here, I will skip how to predict with time. All right, so now I'll move on to a little bit of how we can essentially do thermodynamic modeling for concrete, and I will give you one example of the modeling framework that we have developed. So one of the approaches that you can use to predict concrete performance is using thermodynamic modeling along with the other historical models that were developed, your gel to space ratio model, Powers-Brownyard model, sorptivity models, etc. Right? So in general, the philosophy of any modeling framework is you take your chemistry of the binder, chemistry of the OPC, chemistry of the SEM, reactivity of the SEM, properties of your aggregates, etc. You feed it into your modeling framework and you get your concrete performance. Depending on the concrete performance that you want, you can predict it. For example, porosity, compressive strength, elastic modulus, transport properties, formation factor, calcium hydroxide content, time to critical saturation, freeze-thaw life, pH, blah, 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 blah. All right. So for those interested in details of the modeling framework that we work on, essentially the modeling framework that we work on is, well, I don't want to call it multi-scale, but essentially it moves across from the chemistry to engineering properties. So we start off with the amount and chemical composition of OPC and the amount and chemical composition and reactivity of the SCM in the binder. We then run it through a kinetic, thermodynamic, and pore partitioning model that tells us the volumes of reaction products as a function of time, as well as the volumes of gel and capillary pores as a function of time. We then use a set of well-established theoretical relations, some of which I've shown you in the historical models slides, to then predict the performance of concrete. Right? So some examples are essentially porosity, where we start off with the gel and then the paste and then the concrete, and we are able to predict porosity to within 2% in most cases and within 5% in all cases. Why is predicting porosity important? Because you can start predicting mechanical properties from porosity. So you're able to predict the modulus of elasticity of OPC and OPC plus SCM systems using a very similar relation to what I had shown you earlier, where your elastic modulus is essentially some E0 multiplied by your a function of the porosity. And by the way, this is being recorded, so you don't need to record it on your phone. Okay. All right. You can also start predicting transport properties like formation factor. Again, I don't want to go too much into the equations here, but the basic concept is you start with the gel, you scale up to the paste, you scale up to the concrete using generalized effective medium equations, and then you're able to predict the formation factor, which is an indicator of transport. You can then use that to predict the bulk resistivity of concrete. You can use it to also predict the sorptivity of concrete. And in all cases, you can see that the model does a good job of predicting your concrete properties, right? Sorptivity, formation factor, then freeze-thaw life. We can predict the time to freeze-thaw damage, etc. Diffusion of chlorides, etc. Right? Again, I have 7 minutes left, so let me jump to an application. All right. So now I'll give you one example of the application of these modeling tools that are available to us. Right? Again, I'm not a salesperson trying to sell, hey, this is the only one. This is just to give you an idea of how you can apply modeling tools to essentially better proportion and design concrete mixes, as well as how you can use it to limit your experimental search for feasible mixes for proper mix design. All right. So I'll start off by talking about designing concrete for durability. Right? So generally, most people design concrete for durability by limiting either the compressive strength or the water to cement ratio. Right? Anyone does it differently? Academics need not raise their hands, but anyone from the industry does it differently other than limiting water to binder ratio or strength? No, right? This approach of limiting water to cement ratio and compressive strength works very well for OPC-based concrete. But the moment you start adding SCMs, the relation between your water to binder ratio, strength, and durability breaks down to a certain level. I can give you mixes with the exact same compressive strength, but with vastly different diffusion coefficient of chlorides through the concrete mix, right? So in OPC plus SCM systems, we need to start decoupling your compressive strength and the durability, let us say diffusion coefficient, etc. Right? So the approach that we usually follow is something called performance-based mix design. So in a performance-based mix design, we essentially start by listing the performance criteria that we want to have. So let us say I want to target compressive strength of greater than 28 megapascals. Let us say I want to target formation factor, which is a transport property of greater than 375. This can also be bulk resistivity. Let us say I want a calcium hydroxide content of under 10 grams per 100 grams of binder. And let us say I want a freeze-thaw life or time to critical saturation of greater than 30 years. Okay. Right. All right. So we can use the same modeling framework that I showed you to essentially predict concrete properties and design concrete for durability and limit your experimental search, right? So we have our target performance over here. We can then run the model across a range of water to binder ratios, SCM contents, air contents, aggregate contents, etc. Again, the lecture will be shared. You don't have to keep recording. It'll be on YouTube, all right? So we essentially use the modeling tool and run it iteratively across a range of water to binder ratios, SCM contents, air contents, etc., to predict concrete properties using the model, and then identify a feasible space where all our properties are met. So for example, let us say we want compressive strength. We use the model to predict the compressive strength of concrete. So we run the model across a range of water to binder ratios, SCM contents, and we predict the compressive strength across this range. We want a compressive strength of greater than 28 megapascals. So any concrete mixture below this black line will have a compressive strength greater than 28 megapascals. We then run the model for formation factor. Any concrete mixture to the left of this red line over here meets our target formation factor. Any concrete mixture to the north of this green line over here meets our target calcium hydroxide content. And then we repeat this process for all the listed performance criteria that we have. We then overlay each of these individual contours and find this gray region. This gray region is what we call the feasible space. It is essentially the zone where we meet all of our target performance criteria. So any concrete mixture in this gray region will have a strength greater than 28 megapascals, a formation factor greater than 375, a calcium hydroxide content under 10 grams, and a time to critical saturation above 30 years. Now we have a feasible space. We can start optimizing, right? So now let us say we have an objective function, which is the cost of your concrete mixture as a function of the cost of your materials, the carbon emissions of your materials, and the cost of carbon. So I've taken this value from FHWA's sheet. So we need to revise it with CPWD's rates over here. And I've taken these carbon emissions from the literature. I've assumed a cost of carbon of about $50 per ton. And we can then calculate the cost of the concrete mixes at all of these, okay, it's still not working, within the feasible zone, and calculate the optimum concrete mix that has the least cost. All of this can be done with the modeling tool, right? So modeling tools can essentially help you limit your search for feasible mixes, and they can help you more appropriately design your experiments for maximum bang for your buck, all right? So we're able to optimize, and we can start doing what-if analysis here. So what happens if the cost of my SCM changes? What happens if the cost of carbon changes? Where will my optimum concrete mix fall if I vary my material cost, if I vary my cost of carbon? So if I have a normal cement that costs here and there's no cost of carbon, essentially this mix over here is my optimum. As I increase the cost of carbon, essentially more and more SCM, because cement emits a lot of CO2 emissions. The lesser cement I have in the mix, which is the more cement I replace with SCMs, I have a lower cost of my concrete mix. But at the same time, if I start increasing my cost of my cement again, or SCM, it starts actually coming back down. All right. We can do this in multiple dimensions. I've just given you an example with one, etc. But essentially, this lecture, again, I told Neha and Shashank, I cannot do justice to thermodynamic modeling in one 40-minute lecture. So I just decided to skip with applications and introduction to modeling. So with that, I thank you.